This is problem 6-151. It's on page 326. Repeat problem 6-150 for the air conditioning cost in a dry climate for an outdoor temperature of 28 degrees Celsius. Assume the coefficient of performance of the air conditioning system is 2.3 and the unit cost of electricity is 10 cents per kilowatt hour. Now the previous problem, problem 6-150, is also part of this homework set. And when we worked at what we found is that the volume of the home was 200 square meters times 2.8 meters. This was the floor area times the height. And I didn't multiply those two together separately. It's not all that important. The temperature of the outdoors is given in this problem. It's 28 degrees Celsius. So we were in heating mode in problem 150. Now we're in cooling mode. Now we're in the summer. And the coefficient of performance of the unit, the air conditioning unit, is 2.3. And understand that is QL over WN, right? That's the ratio of the thermal energy pumped out of the home divided by the amount of work required to do that pumping. The electrical cost is $0.1 per kilowatt hour, which is the same thing as 10 cents per kilowatt hour. Temperature indoors was given in the previous problem. It's 22 degrees Celsius. Pressure given before was 92 kilopascals of pressure in the home. And one of the assumptions is that the fan runs and only takes an hour to vent a house full of air. So we're supposed to find out how much that costs. So let's do it. Okay, so if the fan runs for 1 hour and vents the entire volume of the home's air in that hour, it's going to bring in air at 28 degrees Celsius that has to be cooled to 22 degrees Celsius. So we can calculate the amount of thermal energy that has to be pulled out of the home as the mass of air in the home times the constant pressure, heat capacity, times the change in temperature of that air. Now, understand that the mass in the home could be calculated from the ideal gas law as PV over RT. Okay? And so plugging in numbers, 92 kilopascals multiplied by 200 square meters times 2.8 meters, that's just the volume, divided by the gas constant for air, 0.287 kilojoules per kilogram per Kelvin. Multiplied by the temperature. What temperature? 28 or 22? Well, we're talking about the mass of the air in the home. Okay, the mass of the air in the home is maintained at 22 degrees Celsius. So, what that means is that we're talking about 22 degrees Celsius air. Now, be careful. You have to add 273 to get Kelvin to that. Okay? Now, kilopascal times a cubic meter is a kilojoule, and so far, what we've done is just evaluate the mass of the air in the home. The heat capacity of that air is 1.005 kilojoules per kilogram per Kelvin. And so the kilograms go away. And then the change in temperature, the difference, we've got to pull in air at 28 degrees, cool it down to 22. That's a 6 degrees Celsius change. And since it's a change, it crosses off with the Kelvin. So we end up with the amount of energy that we have to pump out in kilojoules. That's about 3,669 kilojoules that have to be pumped out in 1 hour. Now, the amount of electricity we have to pay for to make this happen is the ratio of that heat to the coefficient of performance. Because understand, the coefficient of performance is so called because you can have coefficients of performance greater than 100%, so it doesn't make sense to call it an efficiency for that reason as well as others. But the coefficient of performance just says, well, given that you want to move 2.3 units of heat, you only have to pay for 1 unit of work to do that. This is not really all that strange. We're not talking about destroying energy here. All we're talking about is moving energy, right? So there's energy in the home. It takes less energy to move that energy to outside than the quantity of energy itself. It's kind of like a truck going down the road that's carrying gasoline or diesel or some fuel. The amount of energy required to move that tanker load of fuel from, say, one place to another, from the refinery to the station, is less than the amount of fuel in that tank, at least hopefully, right? But yeah, that's actually the case. So anyway, that's what this is talking about. Basically, we're using electrical energy to move thermal energy. Now, the electrical energy itself also ends up outside. But anyway, so let's continue. So if we plug this in, 3669 kilojoules, coefficient of performance 2.3, then we have to pay for about 1,595.2 kilojoules worth of electricity. Okay, you can also look at this coefficient of performance as converting thermal energy that has to be pumped out to electrical energy that we have to pay for. So anyway, there's a conversion factor. Now, a kilowatt hour is 3,600 kilojoules, so we'd rather see this in kilowatt hours. So let's just multiply, let's see, I'm out of space over there. Let's multiply 1,595.2 kilojoules by the conversion factor for kilowatt hours. In fact, there's 1 kilowatt hour for each 3,600 kilojoules. So the kilojoules go away. And the amount of electricity we have to purchase is about 0.4431 kilowatt hours. Okay, so at a cost of 10 cents per kilowatt hour, you can see you just multiply these two together. So take a tenth of this. And so the amount of cost would be $0.1 per kilowatt hour times 0.4431 kilowatt hours worth of electricity. Comes up to a grand total of about $0.04, which is about 4 cents. That's what it costs to run the bathroom fan for an hour. That's not much. Definitely not worth getting upset about and jumping up quickly to run to the bathroom and turn off the fan because somebody forgot and left it on. Really, it's just not that much energy. It's not that much cost. I shouldn't say energy, but it's not that much cost. A broken leg from tripping over something on the way in your haste would be much more expensive. So this is not much, and it doesn't mean leaving the fan on all the time is a good idea, but it's not that bad. It's kind of interesting. I have a unit in my home that I installed. It's an air exchange unit. Basically, the way it works is it pulls air from the home, runs it through a heat exchanger, and then exhausts it outside. Now, in concert with that, it's also pulling in air from outside, running it across through that same heat exchanger to pick up the thermal energy from the exiting air and go into the home. And the reason I bought it is I like to have fresh air in my home. As a child growing up, my parents had an attic fan, and we hardly ever used it. The problem with the old attic fans, number one, they'd get really dusty. You had to clean them all the time. Number two, they were loud when you turned them on. Number three, the way they were supposed to work is you open the windows. And the problem is they would pull in air into the house from the windows, which was fine, that was the goal. But that air that came in would carry a lot of dust and things with it. And so we just didn't use it very much for that reason. This is a more modern system that not only exchanges heat, okay, unlike that system would have, not only does it exchange heat with the exiting air, but it also filters the air. So it's got a HEPA filter on it, which is really nice. And so my house can always smell nice and fresh because basically I'm pulling in outdoor air most of the time. Even in the wintertime or summertime, I can run this thing. And it's interesting, I've got a non-contact thermometer, so I've actually measured the temperature of the incoming air from outdoors when the outdoor air was relatively cold and only saw about a 2 or 3 degree lower temperature than the air temperature in the home. And so I know that's not costing very much in terms of heat during the wintertime or cooling during the summertime to run. And I can have nice fresh air in the home. It's one of the best purchases I think I've ever made. I really enjoy it. It's a lot better than the old attic fans. I would highly recommend one. One thing I did to avoid more noise, I had it initially sitting in my attic, and it made a fair amount of noise. It would vibrate just a little bit sitting on top of the ceiling joist. And so what I did, it actually came with hooks and things that were designed to suspend it. And so I hung it from the rafters. Now it doesn't even touch the ceiling, so it's very quiet and quite nice. So I would highly recommend it.